Hello, it's Keith here. This is lesson 2 of the Simple series of my 6809 assembly programming tutorials. The Simple series, we create a single assembly file each week, and each one will do a simple task, and the intention is that you could build this into your own little game or program. Now today we're going to be looking at moving a sprite around the screen on the CoCo3. Now this is basically the same as the dragon at some stages. The joystick reading is the same, but the graphics is vastly upgraded, and this is actually, despite what it looks like, it's actually a 16 colour screen. So we've got our little smiley and it's moving around, and we've got the boundary checking so it can't go off the screen. So this is a much more powerful graphics mode, really underused here, but it's just a simple example. And what this means is we can now have better graphics, but it also means we're going to have to deal with the memory banking. The screen is now 24 kilobytes in size, and the way we're going to work with it is we're going to page in that screen in 8K chunks into part of the addressable memory range, and we're going to write our bytes to that area. So we're going to have some tricky stuff with regards to dealing with that, but that's the point of today's example. Okay, well, let's go over to the source code and let's take a look. So some of what you see today is going to be similar to what we saw last time in the dragon example, but there's going to be lots of other things as well. And as the text that just disappeared said, you can get the source code from the website, so please go to my website and download that source code. Okay, well, the start of the program is the same as the dragon. We're building a cartridge, so we've got our cartridge starting at C000. We're turning padding off, which means that the assembler I'm using won't pad to word boundaries, because that causes me trouble with some of my code. It keeps adding zeros to my data statements and things, which I don't like, so we've got that disabled. We've got a ROM footer here, which is the reset vector that defines when the cartridge starts. And so that starts our cartridge up, and then we've got our loading of a valid stack pointer here to get things in a situation we can use things. Now we're going to need to bank in memory to work with the VRAM. Now the CoCo3 has what's referred to as tasks, and this is a sort of task switching thing. You can define two different sets of bank configurations and switch quickly between them, and I think one's designed for the interrupt handler and one's designed for the program itself. So we're going to be using task 0, and this means that the memory map registers from FFA0 to FFA7 are going to define the banks of memory that are accessible via our 6809 or our 6309, depending on the configuration. So that's select what we are going to later use to bank in memory. What we then need to do is select our screen mode. We do that with FF98, and we need to send the correct combination of bits to that. We are using a 256 by 192 16 color screen, which in my opinion is pretty much the ideal screen configuration, if you will, for these retro games. Lots of colors, nice commonly defined screen size. Some systems have 320 widescreens, but a lot don't. 256 is a good size, and it's a very common size, so I think it's a fantastic option if it's available. And then we are defining the other options here with FF99, and that has now selected our screen mode. But what we finally need to do is we need to set the screen base, and what this is this is the memory address of the screen memory, and this isn't the memory address in 6809 memory, this is the actual physical memory address, and so this is more like a 24-bit address. So we're using memory address 60,000, but we divide that by 8, and that is the value that we actually write to the register. We write to FF9D, and that defines the screen base. We're writing C000 here, and that is effectively 60,000. Okay, so that's selected our memory. We now need to do things like show sprites, clear screens and things, but to know how we're actually going to do that, we need to have a look at our screen memory. Okay, so our screen memory is effectively 24 kilobytes in size. Now the bankable areas of the 6809 RAM are just 8K in size. Now we could bank a huge chunk of the memory and get all of that 24K in memory at one time, but that feels a little bit inefficient and unnecessary, to be honest. So what I'm doing is I'm paging in just 8K at a time. Part of the reason for that is I've used the SAM Coupe, which pages in 32K chunks and is very hard to work with because of it. So 8K is much nicer in my mind. So basically, we're going to split the screen into these 3 pageable chunks, and each one is effectively going to be 64 lines because our screen is 192 in total. So what we need to do is basically take the top 2 bits of our Y line and use those as the bank number. So if it's 0 to 63, then we are in bank 0. If we're 64 to 127, we're in bank 1. And if we're in 128 to 190, line 191, we're in bank 2. And that's what we need to select. Now, the way we select a bank is we write to FFA1 for the range we're using. We're using the range 2000 to 4000, and the reason we're using that is because that's outside of the 0 page. It leaves the it doesn't mess with any of our hardware registers, and it doesn't mess with our cartridge or anything. So it's a nice middle ground that we can use there. So that's what we're doing. We need to, of course, define an offset from the screen base, which is a physical address 60,000. So what we're doing there is we're adding hexadecimal 30. So we're taking the top 2 bits of our Y line, we're then shifting them to effectively the bottom 2 bits. That's what all of this is doing. And then we're adding hexadecimal 30, which is the screen base, and that is selecting the correct bank. So that's taking the top 2 bits of the Y line and converting it into and selecting that bank. So we've now got the right bank in place at memory address 2000 to 4000. What we need to do is calculate the offset within that range for the pixel that we want to work with. Now, each line is 256 pixels, and each pixel is 1 nibble, half a byte, so the lines are 128 bytes wide. So what we're doing here is we're multiplying the remaining bits, ignoring those top 2 bits which were the bank of the Y line, so this is 0 to 63 irrespective of the bank. We're multiplying that by 128, and then we're adding the screen base of 2000, which is the logical memory, the 6809 memory that is paged in with that video memory. Then what we're doing is we are adding the X position. We're shifting things around a little bit there so that we can use the add B to X command. And then once we've done this, the Y register is now the memory address within the 6809 memory that we write to get our pixels onto the screen. I know that's all a little bit tricky, but you can just use this and it will work. Now, the only problem is that when you move down a Y line, you do need to check if you've now gone over a memory boundary, because it's possible that you're no longer in the paged area, because, as I say, only 8K of the screen is in it at one time. And to cope with that, we've got a get next line command, and this will move us down 1 line. Now, each line is 128 bytes, so to move down a line, we just add 128. But if we've gone over 6809 logical address of hexadecimal 4000, we're outside of that paged bank now. We've actually moved outside that range, so what we need to do is jump back to the top of the next range and page in the next bank accordingly. So if we were on line 63, the last line of the bank 0, and then we move down to line 64, we'll be outside of that range, so we move back to line 0 and we page in the next bank into that 8K range. That's exactly what we're doing here, incrementing the register here to the next bank, and then we're subtracting hexadecimal 2000 from the memory address, so we're jumping back to that paged in bank in the 6809 logical memory. So that's what we've done there with that get next line command. So these are our commands to work with video memory here. We're going to use those at all times. Now, here is the smiley sprite that we're using. You can see each nibble is 1 color, so that's a color 0. So color 1, that's a color 3, and so on. So you can pretty much maybe see the smiley here. And if you want to create a sprite in the valid format, you can use Sprite Editor. Sprite Editor exports everything for my tutorials. You can go to 6809, you can go to CoCo3 here and save 4/16 color bitmap, and which of those 2 it saves will just depend on these options here. So you probably want 16 color bitmap. Okay, so that's our bitmap, that's our memory functions. And so what about drawing that sprite? Well, here's our show sprite routine here. It's pretty much the same as the last one. We're using an XOR sprite. We're using the EOR command to invert what was already on the screen, and this is so we can very easily remove a sprite from the screen. All we do is we draw it in the same position twice, and the second time we'll remove it. So here we're getting our screen address for our XY position, then we load in our bitmap source. We've got 8 lines, we've got 8 pixels per line, 2 pixels per byte, so 8 divided by 2, that's 4 bytes per line. We load in a byte from our bitmap, we EOR it with the screen byte, inverting it, and then we store it back to the screen. We increment the source and destination data as we do, and we repeat for the bytes of the line. We then use get next line to move us down a line, and when required, page in that next bank, and then we repeat until we've done all the lines. So that is drawing our sprite to the screen. you'll also see we've got a clear screen routine. Now, clearing the screen would usually just mean writing lots of zeros to the video memory, but again, because the video memory is not all paged in at the same time, we're going to have to do something to deal with that. Now, I've done a very crude solution here. I just used my get screen pos function here to recalculate and page in the banks accordingly. You could manually do that, of course, just increment the bank register, but for simplicity, I'm pushing all of the graphics routine functionality into these two functions, so that if something changes, I decide to change the addressable range, the bank I'm using, I don't need to change other pieces of code. So that clear screen routine is just doing the screen in 3 chunks and in recalculating the banks each time with get screen pos. Okay, so that's our graphics routines, and then the only other thing we need to discuss is the joystick, which is exactly the same as on the Dragon. We're using the same code. So the Dragon joystick is an analog joystick, so it can have a range of values, and the way we deal with it is we need to give the digital to analog converter a value to compare to, and it will return a bit depending on whether we are over that value or not. And so what we do basically is we set a value that's 2/3 to the left and see if the joystick is below that, and if it is, then we know we've pressed left, and then we do 1 2/3 to the right, and if the value is above that, well, we know they've pressed to the right. Now this all goes through the keyboard matrix, so we need to turn off the keyboard first, otherwise the keyboard will mess with our values. So that's what we're doing here. We're disabling the keyboard. Now bit 0, when we read from FF00, is the fire button for the first joystick. So we are just shifting 1 bit out of FF00 and we're shifting that into B. We're building up our result in B here. So we've got our fire button there, and then we need to select the x-axis by writing this value here to FF01. We then send our test value, which is this, to FF20, and then we read in and test the top bit 7 of FF00, and that will be the result of the comparison to our test value, and if right is pressed, bit 7 will be 0. We then set a much lower value and we store that, and then we do another test, and that will be a 1 if the direction is left. And these are obviously different. Yeah, we get a bit 0 if right's pressed, but a bit 1 if left is pressed, but we deal with this by flipping some of the bits later on. So that's how we're testing for left and right. We're then changing the value at FF01. You can see it's been changed here, and this is now testing the y-axis, and we use the same test values as we did before for down and up, and that's giving us the range of values. And now what we've got is we've got 1 bit per direction and our fire in the B register, but some of those bits don't match. Generally we're using a 1 if the direction isn't pressed and a 0 if it is pressed, and so to get that we need to flip a couple of those bits. So we're doing that just here. It's a bit tricky, but the long and the short of it is once we've used this function, we now have all of the directions as single bits, and we've simulated a digital joystick, which is a lot easier for us to work with. Okay, so we've got our screen set up, we've got our functions to do our drawing. Now's the time to actually convert all of this into a usable program to move our sprite around the screen. So we clear the screen here. We set our starting coordinates for our sprite. We're using X and Y for the coordinates. We run our show sprite routine to show the initial position of the sprite, and then we read in from the joystick. And then what we do next is we check all of the bits and see if any of the joystick directions are pressed, and if they're not, we just wait until they are. Once they're pressed, we're going to need to process them, but first, to remove that sprite, we need to draw it in the same position as we did before, and that's what we're doing here. We are using the show sprite again, which will remove that sprite, and then we test our joystick directions here. We've got 1 bit for each test here. If the direction is not pressed, then we're skipping over the next section. If that direction is pressed, then we're doing a boundary check. We're checking in this case if the user has pressed up and we're already at the top of the screen, we can't go any further up, so we're just skipping the actual movement. But if they press down and we're already at the bottom of the screen, 192 at the bottom of the screen, and our sprite is 8 lines tall, then we can't go down anymore. Same for left and right. And then to move, what we're doing, there's no inc and det commands, and there's no add immediate for X and Y, but what we can do, it's a bit weird, but we use the load effective address for Y and load effective address for X with an immediate value, and that is effectively an add command for those registers. Quite weird, but it works very well, so that's what we're doing here. So we are increasing and decreasing X and Y here as required. Once we've got down to here, our sprite is updated as needed, so we show the new position, and then we've just got a little delay here just to slow things down, and we jump back to the top and we process our joystick again, and that's what gave us our little example. Let's That's what gives us our moving sprite around the screen. You can see here, and we've got those range of checks in there. Now the idea of this example is that if you're looking to create your own little program and you don't know where to start, well, now you've got an example of reading in the joystick that's hopefully nice and easy. You've got an example sprite routine, and you could of course change this. You could change the sizes. If you were using bigger sprites, you could use different bitmap sources for if you were creating multiple characters. You know, you've got an enemy and a player and things and bullets maybe, and hopefully you can build this into something of your own. And as I say, you can go to my website and get the source code, and as I always say, I'm pretty sure you can't, but if you somehow manage to make the most amazing game the world has ever seen and become a millionaire, well, you don't need to give me any credit for it. You're welcome to it. The idea is hopefully you can make something, or at least have some fun out of these. So please go ahead and do whatever you can with them. That's what they're there for. Anyway, if you've liked today's videos, please hit the like button. If you like the videos, YouTube recommends them to more people, and hopefully they'll like them as well. And if you subscribe as well, that would help me out, because it's a real motivation boost, because it takes me a lot of time to make all these videos. I'm actually making 3 a week at the moment. It takes a lot of time, and basically as soon as I finish one I have to make the other. So yeah, it would help me out. Anyway, I hope you've enjoyed this. I hope you've had some fun with it, and maybe if you go to the website you'll have some fun playing with the source code. Thanks for watching today. If you've enjoyed this video today, please consider supporting my content. It takes 20 to 30 hours a week to keep making these videos. It's basically all I do when I'm not doing my day job, and it's only through the support of my patrons and the other sponsors that I'm able to continue justify doing it, essentially. You can back me on Patreon. I post a weekly update with the latest work on the current projects I'm doing. You can see one here, and also the newest videos. There's a large backlog of videos that are currently only available to the patrons, although they will all be available to everyone later on. And also it's the backers who I ask when it comes to making decisions on how to change the content in the future, what new content to create and things like that. You can see there was recently a survey of the backers, so I can plan next year's content. As well as Patreon, you can now become a member of my channel on YouTube. There's a join button you should see just below this video. You can use that. YouTube backers get the same content as Patreon. I just post it through the YouTube interface instead of the Patreon one. It's the same content every week. Also, if you prefer, you can go to my Teespring store and you can get some Chibi Akuma's merchandise or some Learn ASM merchandise if you prefer, if that's how you would like to back me. Links for all three are in the description of this video below. Anyway, whatever you decide to do, I hope you've really enjoyed this video. Thanks for watching today, and goodbye.